Okay, good morning and welcome back to another session of data structures and algorithm class. My name is Himanshu Gupta and today I'll be talking about the linked list implementation of queue. We already know in the last video, in the, previous videos of data structures and algorithm series, I have covered the array implementation of queue, in which we discussed the various applications of queue, and we know that it is a first out type of data structure. This is the pictorial representation of a queue. In the queue, we take two variables or pointers, rear and front, and we know that deletion is only possible from the front side, and addition will be possible through the uh, from the rear side. If you recall the stack implementation of array implementation of queue, there we have initialized two variables, rear and front, as -1, because our array starts with the index 0, right? But here we are doing the linked list implementation, so we take two pointers, rear and front, and we will initialize rear is equal to front is equal to null. Initially both the pointers are pointing towards null. So what will happen when we create a new node? When we create a new node, suppose this is the new node, we insert some value in this node, suppose say 5, and suppose the address of this node is 1000. So initially this is our rear pointer and this is our front pointer. This both this rear and front will point towards this memory location. R and F both will point towards this block of memory, and both will store the address of the first block like this. Now if I create a new block, initially this the next of this will be null. Now if I create a new block like this will be inserted from the rear side. This will be inserted from the rear side. So what will happen? We will initialize the, suppose this is our node P. We create a node like this. Node P is equal to node malloc size of node, right? So what will we do? We will initialize data of P as value and next of P as null. And then what will we do? See, the insertion is possible from the rear side. So now this new node will become the rear node. So what we will do, we will say that the next of rear, the next of rear is equal to our new node P, and now our rear become, our rear node become this P. So if the address of this node is 2000 and suppose the value here is 7, then now this will contain value 7, and the address now our rear pointer is pointing to, is storing is 2000. So the last value here is the updated one. Now if I again insert a new node in the queue, suppose the address of this queue is suppose the address of this node is 3000 and the value is 10. Then again we will initialize the next of this is as null, and will previously our rear pointer was pointing towards this position. Now our rear pointer will point towards this. So now our rear pointer will store the address of 3000, right? You can see that our front pointer is still pointing towards the first node 5. So this becomes our queue. Like that, the new nodes will keep on adding from the rear side like this, and our rear pointer will be adjusted accordingly. Now if I delete some node, if I try to delete some node, the front node will be deleted. How will we delete the node? How will we delete the node? We'll simply, okay, we'll simply create a temporary node. You just recall my previous video of linked list implementation of stat. Our temporary node is pointing towards the front. It is same as our pop operation in the linked list implementation of queue. So our temp is pointing towards the front, and now what will happen? We'll move the front pointer to the next node. Front is equal to next of front. So basically, see, right now our front contains the address 1000. So this is the memory location with address 1000, and we have created a temporary pointer of type node which also pointing towards this location. Means it also storing this address 1000, and now our front pointer is pointing towards the next of front. That means now it stores the address of 2000. Now what will we do? Now what will we do? We'll take a number value which will store the data of temp, and after that we will delete this location. We will free this location and return the value. Now let's check the display method. In the display method, we will simply check if the queue is empty by simply checking that if front is equal to null. Will print queue is empty and return. Now recall the implementation of array implementation of queue. For traversing the queue, we start from the front element and goes to the rear up to the rear. So here also we'll take a temporary node like this, node temporary is equal to front, and we'll use a loop like this while temp is not equal to null. Then tap, otherwise temp is equal to next of 10. So this is the simple implementation of display method. Now let's, till now we have just see the logic of the implementation. Let's properly write the, let's now properly write the functions. We will first write our structure, type def struct node. This node should contains a variable data to store the data element of queue, and two pointers, sorry, and one pointer. We'll take two pointers separately. Struct node to store the address of next node, and here we have used type def and change the name of struct node as node, right? So after this we will declare two pointers like this: node front. Both should initially point to the null element, rear null. Now we will implement our enqueue operation. Void enqueue, in which we want to insert an element in the queue. We will first check for the underflow. Let's create a new node first. Sorry, overflow. Let's create a new node. As discussed, node n is equal to node malloc size of node. As I have already told you, that overflow condition in case of dynamic memory allocation is very unlikely to happen. If n is equal to null, we will print queue overflow and we will return. So generally such case do not happen. Now what should we do? We'll set the value of our new node, and data of n is equal to b, that we have passed here, and next of new node should be null. Now what will we do? See, there can be two cases. If the node we are inserting is the first node, like if you recall the array implementation of its queue, we need to set both these pointers. If this is the first node, if we have already inserted a first node, then both of these pointers, front and rear, should point to the first node. So if rear, if front is equal to null, sorry, we are inserting the elements from the front side. If front is equal to null, this is our case when we are inserting the first element in the queue. So in this case, what we will do, we'll make front is equal to rear is equal to n. Means both this pointer will now store the will be now storing the address of the new node. Otherwise, else if it is not the first node, then what will we do? We have to simply the next of rear, we like I just discussed in the diagram, the next of rear will be n, and now our rear node, our rear pointer will store the address of our new node n. So this is the Enqueue operation. Now let's see the Dequeue operation. Our Enqueue is just like push operation of the stack, and Dequeue is just like pop operation of the stack. Here we will check for the queue underflow. Queue will be empty when, since we delete the item from the front side, when the front becomes null. This means that our queue is empty and we cannot further remove any element from the queue. So we need to print queue underflow and will simply return -1 here. Otherwise, what we will do, you recall the pop operation of the stack we just covered in the last video. Let's create a temporary node and initialize it with the front node. Let's create a integer variable value and store the value in the data of temp. We can also use data of front, both are same thing. And now set the front as front is equal to next of front, next of front. Now you see we are deleting some node from the queue. If suppose this is the last node, if suppose this is the last node, then after this means both front and rear was pointing to this node, and now front becomes null. So we should also set rear to null because queue is empty now. So here, if it is the last node that we are going to delete, we should handle this case here. If front is equal to null, then we should also set the rear pointer to null. Queue is empty now. Right now that we have already set the values of our front and front pointers, means our pointers, we can now free the space allocated to the temporary storage temp, which contains the address of our front node, our last front node, and now just return the value of the front node that we stored here value. So this is our Dequeue operation. This is our Dequeue operation, and the peak operation is almost same. In peak operation, we just inquire about the front element. So in peak operation, we simply need to first check for the underflow. If front is equal to null, simply vent Q is empty, and return what happened. Just a second. If it is not the case, simply return different element, data of front, and this is our peak operation. Now let's see how we can traverse the queue void display. So in display operation, we'll check if front is equal to null. We'll simply print Q is empty, and we will return from here. Otherwise, you recall that in the stack, in the linked list implementation of stack, what we have done, we had created a temporary node and assigned it with the top. Here we will assign it with the front element, and now we will sorry temp our temporary element temp. So while temp is not equal to null, what we will do, we will print percentage %t data of temp, and we will implement temp as next of temp. So this is our display method. So I hope you now understood the linked list implementation of queue. Now let's run this program in our online compiler. So in order to save time, I have already written the code here. So like we just discussed, the code is exactly the same. This is the structure of our node, which contains a data variable and the node pointer. Then we define two pointers, front and rear, which were initialized with the null variable, null pointer. Then our enqueue, while inserting an element in the queue, we need to check for the overflow condition, though in the linked implementation overflow is very rare. Then we'll simply do as per our discussion. This is exactly the same implementation we just discussed. Then dequeue, peak, and this is our driver code main method. In this in the main method, we enqueue three elements, then displayed the queue, After that, we dequeue the element and display. So let's run this program and check the output. So you can see the elements of our queue are 10, 20 and 30. When we dequeued the element, different elements, the first element comes out, which is 10. Now the remaining elements in the array in the queue are 20 and 30. And when we inquire about the front element using peak operation, it returns us it returned 20. So thank you very much. Hope you enjoyed the video. We'll see you in the next video. Thank you.